Welcome to the sixth lecture in this series on differential equations. So we shall continue with the study of homogeneous equations from where we left off last time. Recall that last time we talked about comparison of infinities. Given two functions f and g, what does it mean to say that f goes to infinity faster than g or slower than g, or f and g go to infinity at the same pace? We discussed some of these issues last time. So let us take one more example on this matter. So orders of infinity and differential equations. So let us look at an innocent looking differential equation. Dy by dx equals y upon 1 plus y into x. We are looking at this differential equation in the first quadrant, namely x bigger than 0 and y bigger than 0. Alright, so equation 2.11 that you see in the slide is a variable separable equation. So you might ask, well, what's there to do? Isn't it all easy? But let's look at these exercises on equation 2.11. First exercise is to find the solution of 2.11 and then to show that the solution cannot escape to infinity in finite time. And then you have to show that the solution tends to infinity at the same rate as log x. What does it mean to say that the solution tends to infinity at the same rate as log x? It means, recall, the ratio y of x upon log x goes to a constant limit not equal to 0. Limit y of x upon log x exists and is not 0. And then the next problem is to look at y of x minus log x upon log x, and you're asked to find the limit as x tends to. If this limit is non-zero, then you will say that y of x minus log x behaves like minus log x, or y of x behaves like log x plus log x. Let's try this amusing exercise. It's not difficult. It appears difficult, but it's not really difficult. The differential equation is a variable separable equation. So what are you going to do? You are going to separate the variables and you will immediately integrate it. Namely, you will divide 2.11 by y, you will multiply 2.11 by 1 plus y, and you will integrate, correct? And you will be integrating things like 1 upon y, 1 upon x, etc. So you will get this equation y plus log y equals c plus log x. It's a very simple looking equation. Now from here we have to answer these questions. You have to show that y of x cannot escape to infinity in finite time. Okay, let us look at this in detail. Yeah, here we are. So we got this equation y plus log y equals c plus log x, right? Now, suppose y of x escapes to infinity in finite amount of time. What does it mean? It means that as x tends to a, where a is a finite number, y of x goes to plus infinity. Well, can that happen? If y of x goes to plus infinity, then log y also goes to infinity, y also goes to infinity. The left hand side of this equation goes to infinity and the right hand side goes to a constant. How is it possible that one side goes to infinity and the other side goes to a finite limit? That will give you a contradiction. So y of x cannot escape to infinity in finite amount of time. I've given a slightly different argument, but it's equivalent to what I just said. What I have done in this slide is that I have just written the left hand side in a slightly different form, y into 1 plus log y by y, right? So y goes to infinity, and last time we have seen that log y goes to infinity slower than y. So log y by y will go to 0. So 1 plus log y by y will converge to 1. So this parenthesis will go to 1 and y goes to infinity. So the left hand side goes to infinity the right hand side goes to finite limit. That's a contradiction. So we have answered the question immediately. We see that y of x cannot escape to infinity in finite amount of time. The next question was, what happens as x goes to infinity? What happens as x goes to infinity? Well, first of all, notice that the differential equation was dy by dx. Let me just write it here for you. Just dy by dx equals y upon x into 1 plus y, right? That was the differential equation. What are the, and where are we? Where x is positive and y is also positive. So what does the differential equation tell you? It tells you that the derivative is always positive. So y is monotone increasing. So if you have a monotone increasing function, either it must have a finite limit or it must go to infinity. There is no other choice, correct? So now, what are the next question? Show that y of x goes to infinity, which means we have to show y of x doesn't go to a finite limit. Look at the equation here. If y of x goes to a finite limit, log y will also go to a finite limit. So y plus log y will have a finite limit. C is a constant and x is going to infinity. So log x is going to infinity. So again, you're going to get a contradiction. So what is it that we have concluded? As x goes to infinity, compulsorily y must also go to infinity. But what does the question ask you? The question asks you to show that y of x tends to infinity at the same rate as log x. Y of x tends to infinity at the same rate as log x. What we have just shown is y of x goes to infinity as x goes to infinity. Log x also goes to infinity as x goes to infinity. Now we must look at the ratio yx upon log x and see what happens to the ratio as x goes to infinity. Well, let's look at that. We have to look at this ratio. Limit as x tends to infinity, yx upon log x. Apply the L'Hopital's rule. Simply apply the L'Hopital's rule. You get y prime upon 1 upon x, or we are looking at the limit as x tends to infinity, xy prime. But what is xy prime? Go back to the differential equation. What is the differential equation again? It is dy by dx equals y upon x into 1 plus y, correct? That's a differential equation. So what is y prime into x? Y prime into x is y upon 1 plus y. So xy prime is y upon 1 plus y. One more application of L'Hopital gives you 1. So we see that y of x goes to infinity at the same rate as log x. The ratio goes to 1. So we say that y of x behaves like log x. In symbols, we would write y of x wiggles log x. The next thing that we need to do is to look at limit as x tends to infinity, y of x minus log x upon log x. Now, how do you know that we can apply the L'Hopital's rule? How do you know that the numerator yx minus log x goes to infinity? Let us look at the next slide. What is y minus log x? Look at this equation. Y minus log x will be equal to c minus log y. C is a constant, mind you. C is a constant, and we know already that y of x goes to infinity. So c minus log y will go to minus infinity. So y of x minus log x goes to minus infinity. So the limit that we are trying to compute is y of x minus log x upon log x. The numerator goes to minus infinity, the denominator goes to infinity, and so we are allowed to apply the L'Hopital's rule. Okay, so we must now apply the L'Hopital's rule to the ratio yx minus log x upon log x. So you differentiate. You get y prime minus 1 upon x in the numerator. You will clear the fractions. You will get xy prime minus 1 and you will pick an x in the denominator. When you differentiate the denominator, it's going to be 1 upon log x into 1 upon x. So the x will cancel out. So what are you left with? We are left with computing limit as x tends to infinity xy prime minus 1 into log x. But what is xy prime minus 1? Go back to the differential equation. Go back to the differential equation. Xy prime is y upon 1 plus y, remember? So that's what you get. So we are led to computing limit as x tends to infinity xy prime minus 1 into log x. But what is xy prime? Remember the differential equation? Xy prime is y upon 1 plus y. So what is xy prime minus 1? Y upon 1 plus y minus 1. You can simplify that and you get exactly what is on the slide. Limit as x tends to infinity minus log x upon y plus 1. Again, it's an infinity by infinity form. One more application of L'Hopital's rule will give you the limit as minus 1. So we have completed the problem. The problem looked a little complicated, but I hope you are now convinced that it's not. We have computed the limit of this ratio y of x minus log x upon log x. This ratio goes to minus 1. So we can say that y of x minus log x behaves like minus log x, or y of x behaves like log x minus log x. Perhaps it's a loose way of saying it. A precise way of saying it is exactly the limit is minus 1. The limit that we have computed is minus 1. So this was an interesting exercise as to how to understand the behavior of the solution as x goes to infinity. So we have got very precise information about the growth of the solution yx. Loosely put, we say that the solution yx behaves like log x minus log x. It is hopeless to try and solve this equation. You might say, why do we do this? Why, we already have the explicit solution, right? We have the solution y plus log y equals c plus log x. But is this solution as explicit as we would like to have it? It's an equation connecting x and y. It's a closed form solution, but y is given implicitly in terms of x. And you would like to solve this and express y in terms of x, but such an attempt is going to be pretty useless. But without doing that, we have obtained a very precise information about the behavior of y of x. What have we done? What does this exercise show? It shows you applications of calculus. We have computed limits. We have used L'Hopital's rule. In the last example, we used calculus to graph the solution. The example in the last slide has been taken from a certain paper of J. Shackle, Growth Orders Occurring in Expansions of Hardy Field Solutions, etc. It seems to be a very scary kind of a title, but there is nothing in this paper that is going to be of any relevance to you. I am putting this reference because this is where I got the example from, and what we have done has nothing to do with the main theme of this paper, and this reference has been put for completeness and correctness rather than for you to look at it. You don't look at this paper at all, it's not relevant to you. Clearly, understanding the behavior of the solution of a differential equation for large times is important because it is going to give you information about the behavior of the physical system. Remember, where our differential equations coming from? Our differential equations are coming from physics, they are coming from biology, they are coming from chemical kinetics, etc. So you want to understand what happens to the state of the physical system as time evolves to infinity. In other words, you want to understand the behavior of the solution for large values of time. And we have just seen two simple examples of it using L'Hopital's rule and the differential equations. One needs to develop theorems, general theorems, because we would like to get this information without solving the differential equation. Obviously, because in real life, you cannot solve the differential equation and then discuss what happens to the solution. The differential equation, the theory of differential equations is about trying to get information about solutions without actually solving it. And so one needs to prove theorems about the behavior of solutions of certain classes of differential equations, and one such theorem was discovered by G.H. Hardy. You know about G.H. Hardy because you have probably seen the movie Man Who Knew Infinity. He is the person who invited Ramanujan to Cambridge. And G.H. Hardy's result was used later by S. Chandrasekhar. In fact, S. Chandrasekhar much later, a few decades later, applied the theorem of Hardy in his study of stellar astrophysics. It's very interesting that a mathematical theorem which was proved in the 1910 found applications much later. Now let us go back to some more exercises on homogeneous differential equations, the y equal to Vx substitution that we have been talking about. So I want to illustrate with two examples from Rainville's book. I already mentioned Rainville's book earlier, and we are going to take two more examples from Rainville's book. Example 6. Y minus square root of y squared plus x squared dx minus x dy equal to 0. Equation 2.12. Rainville gives us slightly different initial conditions. I had taken the initial conditions to be y root 3 by 2 equals half. Solve the differential equation, sketch the solution curves, and sketch the specific one for which y of root 3 by 2 equals half. Problem 7, I leave it to you to work out yourself. We will only concentrate on problem number 6. The first thing to note is this a homogeneous differential equation? Look at the second term, minus x dy. The x term is homogeneous. But look at the first term, y minus square root of y squared plus x squared. This one is not homogeneous. It is only positively homogeneous, and so we must stay in the first quadrant if we are going to use the y equal to Vx substitution. And the initial condition is given in the first quadrant. Remember, carefully chosen. So Rainville asks for the solution only in the first quadrant. So now let us ask what to do in the second quadrant. How would we solve this equation 2.12 in the second quadrant? So you do this exercise 6 yourself because you have to put y equal to Vx and complete the job. It's pretty routine that we already done 2-3 examples of this kind. But we want to understand how to solve equation 2.12 in the second quadrant. So let us see how to solve this equation in the second quadrant. Equation 2.12 in the second quadrant, how to solve. Let us blindly proceed by the y equal to Vx substitution. You just go through the rigmarole and you get x dv plus square root of 1 plus v squared dx equal to 0. And you solve it. You divide by x and you divide by square root of 1 plus v squared. So you must integrate dx upon x, which is log absolute value of x. But now we are in the second quadrant, so x will be negative. What about the other term, dv divided by square root of 1 plus v squared log v plus root 1 plus v squared. The quantity inside the log v plus square root of 1 plus v squared is always positive. So there is no need to put the absolute value there. But log mod x will be equal to log of minus x. So when you combine the two logs together, you get minus xv. But minus xv is minus y. So the solution reads minus y plus root x squared plus y squared equal to e to the power c, which is 2.14 in the displayed slide. But this is wrong. Differentiate 2.14, then you realize that you do not get back the differential equation. So 2.14 is not the solution of the differential equation. So if you proceed blindly, you get the wrong answer. This is serious. We must understand what goes wrong. Remember that I carefully told you that if the differential equation is only positively homogeneous, stay in the first quadrant and all's well. If you move to the second quadrant, caution is needed. Greater caution is needed, because if you simply go through the procedure blindly, you will get the wrong answer. And here is the example. If you differentiate 2.14, what you end up is equation 2.15, which is not the original differential equation. So now let's ask ourselves, where is the flaw? The differential equation is only positively homogeneous. I already told you that. And so the solution procedure as such is valid only in the first quadrant. Let us now do the whole calculation afresh. Let us not believe in the theory that we have developed. Let us rederive the whole thing carefully. What is the differential equation? M dx plus n dy. What is the substitution that we are making? Y equal to Vx. Okay, if you say y equal to Vx, what is dy? P dx plus x dv. This much is okay. Alright, now let us look at the differential equation m of x comma Vx dx plus n of x comma Vx dy. What to do? That m of x comma Vx has been written as m of minus x. X has been written as minus of minus x. Why have I done that? Because x is in the second quadrant, and so minus x is positive. I can pull out the minus x because the functions are positively homogeneous, remember? So I pulled out the minus x to the power k, and I am getting minus x to the power k into m of minus 1 comma minus v. From the second term n, I can pull out an x to the power k because the n term is homogeneous. I know that. There is no problem. And dy is of course v dx plus x dv. So now with this one, what happens to the differential equation? The transformed equation is the last displayed equation in the slide, minus 1 to the power k into m of minus 1 comma minus v dx plus n of 1 comma v into v dx plus x dv equal to 0. So there is a slight difference in the calculation. There are these minus signs floating around. But nevertheless, the last displayed equation is again variable separable. So let's go through it. So proceeding as indicated in the last slide, that is, put back what is the m and what is the n from the differential equation. We get y minus square root of y squared plus x squared dx minus x dy equal to 0. You put y equal to Vx. X is negative. So when x is negative, what is square root of y squared plus x squared? X doesn't come out, mod x comes out. And the second term is no problem. Dy is v dx plus x dv. Now this simplifies to square root of 1 plus v squared dx minus x dv equal to 0. Why is this? Because mod x is minus x now. Mod x is minus x. And the solution of that last one is mod x upon v plus root 1 plus v squared equal to c. The solution is mod x upon v plus under root 1 plus v squared equal to c. Again, c is positive because we exponentiated. Now you rationalize the denominator in 2.16. Rationalize the denominator in 2.16 and you will get the correct solution y plus root of x squared plus y squared. So what is the lesson to be learned? When the differential equation is only positively homogeneous and if you are working in the second quadrant, be careful. Only a mod x will come out in certain places, and that wherever a mod x comes out, you should replace it by minus x, not x. Okay, there are some final comments I'd like to make about these two examples from Rainville's book. If you look at those two equations, let us look at equation 2.12. Let's go back to equation 2.12. 2.12 asks you to find a solution, which means that either y must be a function of x or x must be a function of y, correct? Now, suppose I ask you to find a solution curve passing through a point on the y-axis. Take a point on the y-axis, 0, t. I want to know whether y is a function of x or whether x is a function of y. In other words, it may happen that dy by dx may be 0 or dx by dy may be 0. The tangent may be vertical or it may be horizontal, or the slope may not be defined at all, because you see both the m and the n terms are becoming 0. If you look at 2.12, m of xy is becoming 0 and n of xy is becoming 0 at a point on the positive y-axis. So let us look at this a little carefully. So I want to understand what happens to points on the y-axis. So let us take a point 0, t. And the equation 2.12 reads dy by dx equals y minus square root of x squared plus y squared upon x. Or I can rationalize the numerator and write it as minus x upon y plus under root x squared plus y squared. The first expression is a 0 by 0 form if you assume t is positive. If you take the upper part of the y-axis, if I take a point 0t, it's t positive, then the first expression is a 0 by 0 form. Look at the second expression. The second expression makes perfect sense because what happens to the denominator? Remember, x is 0 and y is t. Square root of y squared is mod y and mod y is t because t is positive. So the second expression puts the value 0 as dy by dx. Now on the other hand, you could write the differential equation as dx by dy equal to x upon y minus square root of x squared plus y squared. Does this expression make sense at points 0, t with t less than 0? So if t is less than 0, then what happens at 0, t? So look at the radical sign. Square root of x squared plus y squared. X is 0. So you're left with square root of y squared, which is mod y. So you get y minus mod y. So what is y? Y is t. And what is mod y? Minus t. Dx by dy makes sense. X upon y minus square root of x squared plus y squared. When you put x equal to 0, you get t minus mod t, but mod t is minus t because t is negative. So you may have to write x as a function of y or y as a function of x along the coordinate axis. Remember that the y equal to vx method fails completely along the y-axis because the variable v has no meaning there. So here are three more exercises on how to find solutions of homogeneous equations by the y equal to vx substitution. Find the solution curve of 2.1 to the same Reinville problem through the point 0, c. We have just discussed that along the y-axis, the method must completely fail because the v equal to y by x, the variable has no meaning. So what substitution are you going to use? Don't say y equal to vx. Here you take the substitution x equal to vy. Take the substitution x equal to vy. Do it the other way around. And the same thing will go through. Modify the method appropriately. So that's how you do problem number 8. Let us briefly look at problem number 9. Equation 2.17. dy by dx equal to x plus y by x minus y. It's a homogeneous equation. Y equal to vx substitution. Of course, along the line x equal to y, the differential equation makes no sense. But away from this line, it makes perfect sense. The differential equation is homogeneous. There's no problem. You can get the answer. Log x squared plus y squared minus 2 tan inverse of y by x equals c. In the next equation, dy by dx minus y by x equals x of y by x. Again, it's a homogeneous differential equation. Y equal to vx substitution will do the trick. Okay, so you got large number of exercises to do. Now let us go a little further. In the next few slides, I'm not going to do any new problems. I'm going to instead look at this homogeneous differential equations and look at a little geometry, the geometric interpretation behind this homogeneous differential equation. It shows some very interesting features. These features are of general interest. They are not going to help you to solve this equation or solve that equation, but it is amusing to see these things geometrically. So let's take a few minutes and see what's going on. You see, what is the homogeneous differential equation? 2.19 dy by dx equal to f of xy. The f is a ratio of n upon m with a negative sign. But m and n are homogeneous of the same degree. So the ratio is homogeneous of degree 0. F of xy is homogeneous of degree 0. So what does equation 2.19 say? That if we take a point x comma mx, if you take a point x comma mx and try to figure out the slope of the tangent at the point x comma mx. Let's do that. So let us see what is the differential equation 2.19 is saying geometrically. Take a point x comma mx. Take a solution curve of the differential equation and take the line y equal to mx. Take the line y equal to mx passing through the origin, and this line will intersect the solution curve at the point x comma mx. So at this particular point of intersection, what is the slope of the curve? Look at the differential equation. Dy by dx is f of xy. But the point is x comma mx. So we have to look at f of x comma mx. But f of x comma mx is f of 1 comma m because f is homogeneous of degree 0. So the conclusion is that the slope of the curve, the slope of the solution curve at the point x comma mx is f of 1 comma m. It only depends upon m, it doesn't depend upon x. So at all the points, so whenever these curves meet this line y equal to all the solution curves intersect this line at the same angle. Let us look at this like a picture. Look at the picture. The picture shows you a line y equal to mx and a family of solution curves for the differential equation. Each solution curves meets this line at a point. The next solution curve meets at a different point. The tangent meets this line at the same angle. The angle of intersection is exactly the same for all the curves. Or take another line. These curves meet this line y equal to mx at these points. These angles are all the same. So all curves of the differential equation cut each line y equal to mx at the same angle. This is not correct. So this is the geometrical meaning of homogeneous differential equations. So now let's go a little further. And this angle, of course, you can easily calculate by using basic trigonometry. So in classical geometry, a family of curves with the property described in the previous slide, a family of curves with the property that they all intersect the line y equal to mx at the same angle. Such a family of curves are said to be similarly placed similar curves, and the origin is called the center of similitude. I shall not elaborate on these words. The property that I just described, all the curves meet each line y equal to mx at the same angle. This property is called curves that are similarly placed, similar curves, the origin as the center of similitude. This is very classical geometry. Unfortunately, it has gone out of vogue, but people who do architecture in those areas, they are very much interested in ideas like similarly placed figures and center of similitude. These things will be more familiar to people in architecture rather than mathematics. But there is one property of these curves. If this family of curves is described as phi of xy equal to 0, then all other members can be obtained as phi of x upon c y upon c. So if you take one member of the family and write its equation phi of xy equal to 0 and replace x by lambda x, y by lambda y, where lambda is a constant, or replace x by x upon c, y by y upon c. So starting from phi of xy equal to 0, you get another equation phi of x upon c comma y upon c equal to 0. In other words, look at the slide. From equation 2.21, you get equation 2.22. So if one of the curves is given by 2.21, then the other curve will be given by 2.22. As you keep changing the c, you will get the family of all curves. So this is a very beautiful geometrical interpretation of the homogeneous differential equations, and unfortunately this is not to be found in most books. I checked many books and I found this in a very ancient book written in 1913. I just wanted to share it with you. And I want to call this the principle of symmetry in differential equations. What does it say? It says that if you take one solution phi of xy equal to 0, a generic solution, not one of these exceptional solutions. Sometimes when you solve differential equation, y equal to 0 is a solution or x equal to 0 is a solution. Those are some special solutions. They are not generic solutions. If you take a generic solution phi of xy equal to 0, replace x by x upon c, replace y by y upon c, and you keep changing the c, you're going to get all the solutions. So this is a I would like to call it the symmetry in differential equations, the principle of symmetry in differential equations. So usually if one knows a solution which is generic, then one can obtain all solutions. So what is the meaning of the word generic? That will emerge as we look at examples. So I want to illustrate this through all the examples that we are seeing. We have solved many examples of homogeneous equations, and now we want to apply this and to each of these examples and to understand this geometry behind this. So of course, what I just said will not work in some cases. Like if y of x is 0, if you have a 0 solution, you replace y by c, again you get the 0 solution. You don't get anything else. So the 0 solution will be an exception. It will not be a generic solution. So that's why the word usually is being put, and I'm not putting this as a theorem, because the moment you want to put it as a theorem, it has to be stated with utmost precision, and I'm not stating it with utmost precision. So I'm not elevating the statement to a status of a theorem, and I'm not going to prove the theorem either. So for the same reason, we shall not discuss the proof of the result quoted above. Let's look at a different aspect of this symmetry. So let us take a non-zero real number t, and let us put capital X equal to Tx, capital Y equal to Ty. 2.23 is called similarity transformation or a homothety. 2.23 is magnification in the x direction by factor of t, magnification in the y direction by factor of t. It is like enlarging the picture. You have a picture, you've got a passport size photograph, and you want to enlarge it. You do the same magnification in the x and the y direction. You get a larger picture. So that's a similarity. The two pictures are similar, like similar triangles. The sides are magnified by the same amount. So that's a similarity transformation. So go back to the differential equation, dy by dx equal to f of xy. F is homogeneous of degree 0. What happens when I make the substitution 2.23? Apply the chain rule. D capital Y by D capital X equals D capital Y by D little y. But what is D capital Y by D little y? T. And then D little y by dx. And then dx by D capital X. But what is dx by D capital X? 1 upon t. The t and the 1 upon t will cancel out. So D capital Y by D capital X is the same as D little y by D little x. What happens to the right hand side 2.24? When you replace little x by capital X upon t and little y by capital Y by t, the t disappears because f is homogeneous of degree 0. So what happens, a new differential equation that you get 2.25 is the same as the old differential equation 2.24. The differential equations 2.24 and 2.25 are identical. So we say that the differential equation 2.24 is invariant under similarity transformations, or it is invariant under homothety. So the principle of symmetry says that if phi of xy equal to 0 is a solution, then phi of cx comma cy equal to 0 is also a solution, and all solutions can be obtained from a single solution provided you choose a generic choice of solution. Stated differently, homothety takes a solution to a solution, or the set of solutions is invariant under homotheties. Yeah, these things are not exactly relevant to the JEE examination perhaps, but it is educative and I think one should know this. So let's look at this through the examples that we already studied. So let's take the first differential equation that we integrated. 2xy dx minus x squared minus y squared dy equal to 0. Equation 2.4 we studied. in this chapter. What is the solution we got? X squared plus y squared minus cy equal to 0. Take c equal to 1. Take c equal to 1 and let's look at the special solution x squared plus y squared minus y. Let's see. So, phi of x upon c, y upon c will be what? It will be x by c the whole squared plus y by c the whole squared minus y upon c. So, phi of x upon c, y upon c is equal to 0 gives x squared plus y squared minus cy equal to 0. You see, we got all the solutions. We took a specific solution, phi of xy equal to x squared plus y squared minus y equal to 0. This special solution we took, replaced x by x upon c and y by y upon c, and we got all the solutions. So, you see, we are given the illustration of the principle of symmetry. To the next example, 2xy dx plus x squared minus y squared dy equal to 0. What was the general solution we obtained? 3x squared y minus y cube equal to c. Take c equal to 1. You can take c equal to 5 if you like. Doesn't matter. But if you take c equal to 0, it will not work. So, when you take c equal to 0, you get an exceptional solution. You get a solution which is not generic. So, take c equal to 1, you get phi of xy equal to 3x squared y minus y cube minus 1. So, all solutions are obtained by replacing x by x upon c, y by y upon c. Let us take the third example. Another example that we solved was y dx plus x into log y minus log x dy equal to 0, for which we got the solution y minus 1 minus log y plus log x equal to 0, which was equation 2.10. So, again we have got a phi of xy. What is phi of xy here? Phi of xy is y minus 1 minus log y plus log x. So, let us see whether we replace x by x upon c and y by y upon c and see what happens. Let us do that. So, what is our phi of xy in this case? Phi of xy in this case is y minus 1 minus log y plus log x. Here, of course, we have to work in the first quadrant, but never mind, the principle works even in the first quadrant. So, phi of x upon c, y upon c is what? It will be y upon c minus 1 minus log of y upon c plus log of x upon c, which will be 1 by c into y minus c log y plus c log x. So, when you put phi of x by c, y by c equal to 0, you get y minus c log y plus c log x equal to 0. You check that this is the general solution. Take the next example from Rainville's book. Y minus square root x squared plus y squared dx minus x dy equal to 0. We got a solution.
Phi of xy equals y plus square root of x squared plus y squared minus 1, but only in the first quadrant, since the differential equation is only positively homogeneous.
Consider the homogeneous equation xy dx minus x squared plus 4y squared plus 4xy dy equal to 0. Taking two more examples from Rainville's book. Observe that if you take phi of xy equal to y plus x, then phi of xy equal to 0 is a solution. Namely, y equal to minus x is a solution, but then you are not going to get all the solutions from here. Because if you take y plus x and if you replace y by c and x by c, then phi of x by c comma y by c equal to 0 is again the same solution. So you get the same solution. You don't get anything new. Does this contradict the principle of symmetry? No. Solve the equation 2.26 in general and identify the special solution. Well, 2.26 is a homogeneous equation. Make the y equal to vx substitution. Get the general solution. The general solution is displayed in red in this slide. In this solution, if you put c equal to 0, what do you get? You get y cube into x plus y equal to 0. So that's why you see x plus y is a special solution. And now you understand why it is really special. A last example, you look at the differential equation x squared dy minus 4x squared plus 2y squared plus 7xy dx equal to 0. We see that phi of xy equal to 0 furnishes a solution for each of the choices x plus y and 2x plus y. Namely, y equal to minus x is a solution and y equal to minus 2x is also a solution. If you start with these solutions and do the x by c, y by c trick, you will not get all the solutions. You will get the same solution again. So these two solutions are not generic. Why are they not generic? Solve 2.27 in the usual way. Y equal to Vx substitution, get the general solution and see what happens. Solve the differential equation completely and try to figure out what's going on. And the answer is given to you. It's x squared y plus 2x cube minus cx minus cy. So what happens when you put c equal to 0? When you take c equal to 0, you get x squared into y plus 2x equal to 0. So y plus 2x is a very special solution. Okay, so y plus 2x is a special solution. But why is x plus y a special solution? Look at the last display, last line in the display. You divide by c. You divide by c, then what happens? Let's see. You see, the differential equation is x squared dy minus 4x squared plus 2y squared plus 7xy dx equal to 0. Okay, I am saying that y equal to minus x and y equal to minus 2x are both exceptional. They are special solutions, not generic. Why am I saying this? You have to do this as an exercise. It's an exercise for you. Solve the differential equation completely. Solve the differential equation using, of course, the y equal to Vx substitution. Okay, you get the solution. The solution reads x squared into y plus 2x minus c into x plus y equal to 0. That's a general solution. Now, when you take c equal to 0, that gives you y plus 2x as a special solution. But why is this one a special solution? You see, you divide by c and let that c go to infinity. And what do you get? You get x plus y equal to 0. So you see that y equal to minus x is also a special solution. So there are these exceptional solutions which are not generic and they will always be there. But if you leave out these exceptional solutions and pick up a generic solution and replace x by x upon c and y by y upon c, then phi of x upon c comma y upon c equal to 0 will generate all the solutions. This is a very beautiful part of homogeneous differential equations. Unfortunately, this is not discussed in books, so I thought I must really point out this intrinsic geometry that is present in this chapter. I think with this we will close this lecture and this chapter also. Next time I am going to start the new chapter on linear and Bernoulli equations, and after that we will probably take a concluding lecture. and finish the series of lectures. Thank you very much.